So we are going to start, as I announced in the email, the new module, which is on discrete time signals and systems, right? So the previous three modules have all focused on continuous time signals. And remember we said that the continuous time signals, the thing that characterizes the continuous time signals is the fact that it has the independent variable is time, and that independent variable time is actually continuous, so that the function or the signal takes on continuum of values over the real number line, right? Now, as opposed to this, we're going to shift gears now and talk about another important class of signals and systems, which is that of discrete time signals and discrete time systems. So any ideas? When I say a discrete time signal, I mean, what comes to mind, right? If I just by hearing the term discrete time signal as opposed to continuous time, what do you think would be different in a discrete time as opposed to a continuous time?
There would be discontinuities, more discontinuities.
Okay, what do you mean by discontinuities, Tala?
It would be zero. So like, like, there will just be focusing, and बीच में zero हो जाएगा काफी points पे.
Okay.
And on you be like taking care of certain like 8 point पे, I guess, just discontinuity. वो policies only after every.
All right. Okay, so it's almost there. Anyone else? Any thoughts on what do you think discrete time signal is going to be? So the key difference is in the fact, so that people point out to this and somewhat in the chat window as well. The key difference is when I say continuous time is a time in which the t independent variable takes on values over the entire number line, right? Over the entire continuum of values on the real number line, right? And that's where discrete time signals are different. How? So discrete time signals are those signals which take on, or which are defined to take on values over only a discrete set of the independent variable, right? So that's essentially what is different. And I'm going to start with some examples to illustrate this concept further. So discrete time signals. So discrete time signals are those that are defined for a discrete set of or discrete values of the independent variable. And let's talk about some example. Right, so here are some examples. So let's say relevant or apt an example, considering the fact that we are in a pandemic, right? The statistics that you would hear every day in the morning, when you wake up, that's the first thing we check in the morning anyway, right? So many of us, I do, right? I just open up an app and see what are the confirmed number of cases today and what is the number of deaths today, right? And if you look at a graph of those confirmed number of confirmed number of cases over the entire recording period, which is more than a year now, right? What kind of a curve do you look at? Is that curve really? Have you seen? There's a COVID website, a Pakistani website. There's lots of other data. News articles. You would often see what are the trends, right? But when you see that graph, or when you see that signal, which I'm going to say is a signal, how is that different than, for example, a voltage signal that you're familiar with, right? The way it's different is that it takes on values over a discrete set of discrete values of the independent variable, right? So the x-axis here, as far as the confirmed number of COVID cases, the daily number of confirmed cases, right? So this is COVID confirmed cases, or I say daily COVID confirmed cases, right? So on the x-axis, you have days here, right? Let's say this would be some day here, another day here, another day here, another day here, and so on and so forth. So let me use a different colors. And one day here, another day here, another day here, another day here, right? So this is, um, let's say this would be day one when the pandemic started. This would be day two from the time that the pandemic started, day three and day four, and so on and so forth, right? And the values that you're going to see, I mean, arbitrarily, for example, I mean, it started out small, you say, started out small, and then exponentially started increasing, right? So there was an exponential increase, right? And perhaps at some point, it started decreasing again as well, right? So this curve that you see here is a discrete time. I would say this is a discrete time signal because it once again conveys information about some physical phenomena, right? It is a physical phenomena, which is the confirmed number of cases, but it is conveying that information for a discrete set or discrete values of the independent variable, which over here is time, right? So this axis here is time, or which in this case is days. Okay? So this, I would say, this is a discrete time signal. Now, there are many, many other examples that I can cite, right? Any other thoughts that comes to mind? कि और किस किस्म के discrete time signals हो सकते हैं? जी हसन.
सर टेक्निकली जो हमारे पास कंटिन्यूअस ग्राफ आते हैं, लाइक लेट्स से वोल्टेज का कोई सिग्नल आ रहा है,
Yeah.
in the in principle वो भी discrete ही होता है ना, because the measurement device you have has a interval as well. वो हमें continuous नजर आता है. So
Okay, good.
practically वो continuous होगा.
Right. I'm going to come to that in just a while and remind me again, right? So let me talk about these examples, then I'm going to come to this point. There was an excellent example in the chat window, which is the number of the runs in 50 overs, right? So you take up on the x-axis, you have overs. I mean, that's something brilliant, Asad. I mean, this is never something I thought about this, right? So you have on the x-axis, you have the number of overs, 1, 2, 3, 4, all the way up to 50. And you have the number of runs scored in each over, right? Or for that matter, the number of runs scored on each ball. I mean, that would also be a discrete time signal, right? Excellent. Masna, do you have a point? So this is...
Yes,
let
sir.
me
I
write this
wanted
down. Ji, boliye.
Sir, are the music recordings or voice recordings discrete signals too? Because I read they're sampled.
Yes.
Or something like that.
So this is related to Hassan's point, Masna. I'm going to come to
Yes.
this and remind me again when I talk about sampling, just very briefly, right?
Okay, sir.
Right. So here's, I mean, something which is related to this class here as well, right? So which is the number of students attending a class as a function of the lecture number, right? For EE310, for example, right? And I can, perhaps there are some trends here, right? So thankfully, today is an upward trend, right? So this is lecture number here, right? And I'll say lecture number 1, what was the number of students attending? That would be some number. And then lecture 2, lecture 3, and goes down perhaps, right? And goes up. So it's a sort of, let me keep this random, right? And I would ideally like to see just this as a flat maximum values, right? So this once again is also a discrete time signal. And Hassan Hassan Shabir points out the grades scored by a student in a course. So I would say, okay, so the grades or the final, let's say grades ke bajaye, aggregate, right? And now the x-axis is no longer physical time, right? So this is student index, right? And say कि student number 1 has this score, student number 2 has this score, student number 3 has this score, and so on and so forth, right? This would also be a discrete time signal. There was a hand raised.
Yes, sir. So I raised the hand, sir. I just had a question, sir. Is there like a fit like criteria कि यहाँ तक जो है ना a signal is discrete? Because technically, if we keep increasing the precision, won't it just keep becoming more continuous?
Yes, but as long as that precision is finite or greater than 0, okay, the separation is greater than 0, it would still be discrete according to the definition. Okay? I mean, when it goes to 0, I mean, things happens in the limit. I mean, that's maybe not talk about that yet. Okay? All right. One final example I want to talk about before I move on. So, and the reason is because all of the examples that we've talked about, they're all positive, right? They're always stay above 0, right? So let me just say, KG, if you're running a business, this would be a discrete time signal. The profit earned per month, right? So here on the x-axis, you have the month, and I'm going to say there's an index, right? So the first month, the second month, the third month, and you may have a profit, and in some occasions you may have a loss, which in turns out the profit is just negative. That means it's actually was corresponding to a loss, right? So the point here is, okay, the independent variable takes on values over a discrete set. It's not continuous, right? So these are discrete time signals, right? So these are essentially discrete time signals. Now, an important point here is just like in continuous time signals, which is the independent variable may not necessarily be time here. May not be time, but I mean, for simplicity, because of the reasons that we cited for continuous time as well, we will refer to the independent variable as time. As an within this quotation. So this may not be physical time. And just like the student aggregate, right? So you say student number, ye average, yeah, final aggregator, right? And that was not really time, but that's an independent variable nevertheless. And for purposes that we highlighted in the very beginning of the course, we are going to still refer to that independent variable always as time, right? Now, what is the important point here is, what is a notation we're going to follow to describe discrete time signals? And that notation is X, and then instead of that parenthesis that we were using for continuous time signals, over here we're going to be using these square brackets, right? And the index within these square brackets refers to the independent variable. So this is the independent variable here. So the n is the independent variable. And the key difference as far as our notation is concerned from continuous time is the fact that this n can only take on values over the integer set, right? So it can only be integers, right? And that's a mathematical construction that we have. I mean, in principle, discrete time signals are all signals, okay, they're just defined for some discrete values of the independent variable, right? However, we could always do some operations on them and reduce them to a form where this independent variable are always integers. And that's what we're going to follow from here on, right? So that mathematical abstraction is going to be the fact that from here on, all discrete time variables or discrete time signals are going to be represented as a function of the independent variable n, where n takes on values from the integer set. Okay? As an example, so here's where we start talking about abstraction now, right? So as an example, if I tell you that I give you a discrete time signal, which is x of n, right, equal to 1, which is equal to 1 from all values of n which are less than equal to 2 and greater than equal to -2 and are 0 otherwise. Right? So this is once again, this is where the abstraction now starts. Now we're not interested in what this physically represents, but rather we're interested in finding or learning the mathematical tools that are essential to deal with practical signals, right? So that's where we're headed, right? So if I give you this signal x, right, which is a discrete time signal defined for an independent variable n, which takes on values over the integer set, and I then ask you, Kiyar, plot this or sketch this signal, what would this signal look like? if I can have somebody try to answer this, right? So the x-axis is n. What does x of n look like? What does the graph look like? G Masna.
Sir, a a a bar a line from 0 to 1 for every one step from -2, -1, 0, 1, 2.
Okay, Masna.
And
So
the
when you
rest is
say a
0.
line, let me just stop here. When you say a
Vertical.
line, could that be like something like this?
Yeah, it could. No, I think they are vertical lines
Vertical
after
lines.
every one
Okay.
interval.
So this is not possible, right? Because I mean, when I plot this out as a function of the independent variable, this actually corresponds to a continuous time signal, right? It has to be discrete time, right? So this is now, and what it actually is, what you refer to, is okay, it's going to be equal to 1 for n equals -2, and it's going to be equal to 1 for n equals -1. It's going to be equal to 1 for n equals 0. It's going to be equal to 1 for n equals 1. And what about n equals 2?
It's not going to be 1. It's going to be 0 because
It's
it's
going to be 0.
less than, not less
Good.
than equal to.
Right? So this is all zeros for all other values of n. And this is your x of n. Right? This is x of n. And this is a sketch of that x of n. Right? Good. All right. Any questions here? Right. So what I want to do next,
सर सर जो
बताया।
फोरियर सीरीज में हमारे ए के एस वाला था वो भी डिस्क्रीट होगा
Aha, excellent, Daniel. So that's an excellent point, right? So would somebody like to answer? Daniel's point is the following, which is okay, when we talked about Fourier series, the Fourier series coefficients, Daniel claims, if I understand him correctly, was that a discrete time signal? Would somebody like to respond to that? G. Ibrahim?
Sir,
Sorry, Manur, people have raised their hands, so I'm going in the order. Ibrahim, you go ahead.
जी सर आई थिंक ए केस जो है वो तो डिस्क्रीट ही है मगर हमारा सिग्नल वो फिर भी कॉन्टिन्यूस ही रहता है ना कि एक को मल्टीप्लाई कर रहे हो तो इंटीग्रेट कर रहे हो
Yes, excellent, right? So, but the series coefficients, right? So let me just point out a note here, right? So a note, the continuous time Fourier series coefficients, and what they look like? I mean, we represented these AKs, right? Right? And where this K was actually a part of the integer set, right? So if I were to sketch this out as a function of K, I would actually get the discrete time signal. I mean, this would be a 0 here, and then this would be a 1 here, and so on and so forth. So yes, you're right that was actually a discrete time signal, except that this K, right? So I mean, we're using the notation was slightly different. I mean, we were using A underscore K, right? Or under A subscript K, sorry, right? As opposed to this notation that we're using, there's a parenthesis, but otherwise the concept is the same, right? Okay, Manu, did you want to ask a question or do you want to answer?
no, sir, I want to answer it, and yeah, I was wrong, so I'm glad I didn't.
That's fine. I still noted down your CP.
Okay, thank you, sir.
Right. All right. So that's an important point. Excellent. So what I want to say next is that coming back to some of the points that Hassan and Masna raised at the beginning, which are about sampling. Now, it turns out that lots of signals that we come across are in fact discrete inherently, right? Some of the examples that we talked about in the beginning, right? COVID numbers or number of runs scored per over or per ball. I mean, that is inherently discrete. There's nothing continuous about them. But then there's a large class of other signals which are actually continuous, but they are discretized, right? And why are they discretized? They're discretized, as Masna alluded to in the beginning, because I mean today's age is the age of computers, right? And those computers need to work with signals. I mean, for example, if you want to work with an audio signal in a computer, and I think that's an example that Masna cited, right? If you want to work with an audio signal in the computer, right? And let me plot this audio signal out for you. Let's, as an example, right? So let's say this was a continuous time signal, which was XFT, and it looks something like this, some arbitrary shape that it had, right? And let's say this was my voice. And I then asked you कि यार इसको कंप्यूटर के अंदर लेके जाएं और कंप्यूटर के अंदर इसको कुछ प्रोसेसिंग करें, right? Now, do you see any problems with this? I mean, for problems of associated with using a computer to process this X of t, right? So let's say this was X of t. Ji Hamza.
सर सिग्नल थोड़ा बहुत लॉस्ट हो जाएगा.
नहीं, सबसे पहली तो बात यह है कि इसको आप प्रोसेस कर सकते हैं, नहीं कर सकते कंप्यूटर को, इस कंटिन्यूस टाइम सिग्नल को. Let's see who raised. अच्छा जी. Right, so Umar, go ahead.
सर वो कंप्यूटर पर जो है वो प्रोसेस करने के लिए पेयर्स चाहिए होते हैं, मतलब एक्स और वाई वैल्यू पेयर्स. तो आई गेस उसके लिए हमें फिर पहले उसकी सैम्पलिंग करनी पड़ेगी, तब वो उसको कर सकेगा.
X and Y pairs. I mean, the inherent reason why you use sampling is not because you need X-Y pairs. There's another strong argument behind that. And let's see. Roshin, आपने हाथ खड़ा किया था.
Sir, I was going to say that the computer can only understand binary anyway, so I wouldn't be able to interpret the continuous signal.
Computer just processes binary. So that's a further step. I mean, let's say if you had a computer which was able to, I mean, some genie tells you कि यार ये binary नहीं, बिल्कुल floating point values भी, I mean, exact values भी कर सकता है. Even then, there's a big problem here. Talha?
My point was binary हो जाता.
Binary
since you can, there are certain analog computers as well जो कि analog processing कर देते हैं.
So you know, with the simplest analog computer, or one of the analog computers that you would have seen probably in the videos, is that Michelson's harmonic analyzer. I mean, that's an analog computer. Okay. So, and Turing, Alan Turing, when he tried to make that machine of his, or code decryption machine.
Enigma?
Yeah, there's a movie for that as well. Enigma ko break.
Yeah, I've seen it.
Right. So it goes through. There was all gears. There was actually analog. Right. Hassan, Shabir?
Yeah, sir, I think the signal contains noise as well, so that's why we need to sample it first before the computer can process it.
Right. Hafsa?
Sir, I think we need values at particular values as well, like at proper intervals, so that the computer can interpret it in a way.
All right. Okay, particular values. Why would you want that particular values?
Sir, because this graph is spread out and we don't know what the values would be unless we plot them out.
Let me address SKG. If you were to, for the computer to know exactly what X of t was, how many values would the computer need? Right, if you just start counting, right? So in order to specify, I mean, you don't have a functional description of this, by the way, right? There's a limit to the processing power. Excellent, right? So there's a limit to the processing power, and the number of values that you would need are actually infinite in number, right? Why? Because not only would you want this point here, this point in blue, uske bilkul sath jo pada hua hai, right? Infinitesimally small, infinitesimally close together. You'd also need that, right? So in order to completely specify the smooth continuous curve and completely provide that to the computer, you need each and every point on this on this curve to be available to the computer. That's not happening, right? Your computers have finite processing powers. Your computers have finite processing powers, which will not allow you to give all of this information as is to the computer. Okay? Daniel, did you have a question?
Yes, sir. मेरा सवाल है कि सर ये signal non-causal है?
हाँ, so non-causal signals, yes, it's a non-causal signal.
तो फिर सर वो तो real नहीं होता ना?
हाँ, लेकिन I mean, as far as abstraction is concerned, we're okay, right? चलें. Okay, so let's. Right, so that makes. अब ठीक है? Right. So the point I want to make was, okay, in order to make sure that you are within the processing limits of your computer, what you would do is you would sample this after every certain amount of time, right? So you would say, yeah, let me sample it at time t equals 0, and that's the value that's going to be put to the computer. Then let me sample it after a certain time duration, and this is t sub s seconds, right? And this is the value that's going to be forwarded to the computer at 2 times t sub s seconds. This is the value that's going to be forwarded. This is the value that's going to be forwarded. This is the value that's going to be forwarded, right? So it's 3 times ts. This is 4 times ts, and so on and so forth, right? So essentially what you're doing is it's like the things are going on in the real world, but you're sampling in the sense, I mean, think of this as the computer, what it does is it opens its eye at time 0 and sees what the signal is, and then closes it again. It closes, and then after capital T seconds, it opens again and see kahan pe pahunchi hai, and just samples it or memorizes it, and then closes it again, right? So you're looking at a scene, and then you're sampling different parts of the scene at regular intervals. This process is called sampling, which is done by your computers and your processors and microcontrollers that you would already be using, right? So this is the sampling process. I can represent the sampling process mathematically very, very nicely. Any ideas how I can do that? So I'd say, KR, this thing that I get after the sampling process, this green signal is actually a discrete time signal, right? And let's say and this is time 0. I say, okay, let me represent that discrete time signal as the following, where instead of the continuous time, I have n, which is an integer, and at time n equals 0, this is going to be this value, n equals 1, ye value, then slightly smaller, and then ye, and so on and so forth. And here, and this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. And this is x of n, and this pink thing is x of t. The question here is, what is that relationship between x and x of n and x of t? जी मानूर.
सर आई गेट कि हम इंटीग्रेशन यूज कर सकते हैं इसके लिए, लेकिन माय क्वेश्चन इज कि इंटीग्रेशन में तो वो पूरा एरिया कंसिडर हो रहा होता है, लेकिन इस सिचुएशन में वी ओनली वांट टू कंसिडर जहां पर आपके इंटीजर नंबर्स आ रहे हैं, राइट? तो फिर हम उस चीज का सम नहीं ले सकते? फॉर एग्जांपल हमें उसकी शेप का पता है, एंड देन वी जस्ट टेक द सम फॉर लाइक फॉर एग्जांपल 0 to 6 अगर हम ले रहे हैं 0 1 2 3 4
What you're talking about is कि क्या उसको हम सम को स्टोर कर सकते हैं, नहीं कर सकते? Is that what you're saying?
Yes.
Right. So that could be one way. That could be one way. You say you look at a certain interval, and within that interval you integrate and then store that integration value.
Yes.
Right. But then and that could be one way, but that's not what is used. That involves an integrator that adds complexity, and that's harder to implement. Right. And the theory behind what we're going to be doing here, sampling, that is so elegant that you don't want to do anything else.
Okay, sir.
Okay. Masna, you wanted to say something?
Sir, can we use the delta function?
Okay. You can use the delta function, but the solution is much simpler.
Or the Fourier series coefficients, because don't they do the same thing?
Yeah, but the signal is not periodic, right? So I just want to say, do this. मैं इसके अंदर क्या करूं? So let's say this is, so let me use another notation. Let's say this is X continuous and this is XD, right? So the discrete signal, उस continuous signal को मैं क्या करूं? जी मूसा?
Sir, what if we like take impulses? और फिर हम impulses को multiply कर panel के साथ? Won't that give like an answer?
Yes, that's one way. That's one way, and that's a harder way. There's a much easier way, जो कि यहाँ पे सामने लिखा हुआ screen में, right? I just want to put something here, which is a function of n, and is a function of. Sorry, let me elaborate on this, right? So what do you see here? You see, this is x of. Let me see. Right, t equals n. Almost there, right? So when I say, what is xd of 0? That's actually equal to xc of 0. What is xd of 1? That is xc evaluated at ts, right? And what is xd of 2? That is the continuous signal evaluated at 2 times ts, right? What is xd of 3? That's xc evaluated at 3 times ts, right? Do you see a relationship? N times ts. Excellent, right? So this here is nothing but n times ts. And thus, I mean, you could do that multiplication with the delta functions, and that would work, and that's valid, but this is much easier, right? As far as, so this is the sampling process. And here, ts is called the sampling period. And fs, which is equal to 1 upon ts, that's the sampling frequency. Right? So sampling frequency is the number of samples that you take per second, and sampling period is the difference between the time difference between two adjacent samples, right? So, I mean, for those of you who would have recorded your audio sometime, or I mean, used Windows audio recorder, या sound recorder, या MATLAB में अगर कभी record किया हो, तो did you ever come across something called the sampling frequency? The sampling frequency is typically 48 kilohertz for wave files जो record होती हैं. अगर आप अभी record कर रहे हैं 48 kilohertz पे record होगी. That is this sampling frequency, which says that this sound wave, whatever is coming in, is going to be sampled 48,000 times per second. That's what is meant by sampling frequency of 48 kilohertz. Now the question here is, is there some loss in information in that discretization process? So is there loss in information? Due to discretization? Kya khayal hai? Yes. Right? And I mean, that's very obvious, should be obvious, because I mean, you don't know what's going on in between, right? You don't know what's going on in between. I mean, between two adjacent samples. Ji Masla?
Sir, is that the reason why our sounds are slightly different in a recording rather than what we hear ourselves? मतलब थोड़ा सा different आवाज आ रही होती है.
Right, मसला इसलिए जरूरी नहीं है ये बात तो इस ऐसा कि जी oftentimes we're not used to hearing our own voice from a third party source. Right, so a real test for that would be what? The real test for that would be कि आप बोल रहे हैं और कोई बंदा सुन रहा हो, और फिर आप अपनी आवाज रिकॉर्ड करें और फिर बंदे को सुनाएं, and फिर उससे पूछें यार दोनों सेम है या डिफरेंट है. That would be the true test. But otherwise आप अपनी आवाज हमेशा यहाँ से सुन के यहाँ से जा रहे हैं, इसका रिस्पॉन्स कुछ और है. Right? But actually, Mehreen pointed out something here. The degree of loss depends on the sampling frequency. Right? The degree of loss depends on the sampling frequency. And the other point, same as Masna, yes, Masna, I would tend to actually agree, right? So I've heard you in person, and I'm hearing you on the call. They're more or less the same.
Yeah,
right?
Okay, sir.
Okay. So, but the point that Mehreen was making was really interesting, which is, KG, it depends on the sampling frequency. And I'm sure what she meant was, if you increase the sampling frequency, the degree of loss is going to decrease, and if you and vice versa. Okay. But you know what? The answer to this is not necessarily. And I'm going to leave it like this. Right? It turns out, and we may not get to this, or I may just say something about this one in the lecture or the next lecture after that. It turns out, and these are results developed by many years ago, decades ago, or actually centuries ago, perhaps, by Nyquist and by Shannon, decades ago at least. It says, KG, it turns out, KG, if your sampling frequency satisfies a certain criteria and your signal satisfies a certain constraint, there is no loss because of the sampling process, right? And that's a very counterintuitive result, but we will have something to say about this a little while later, right? Yes, the same channel, Hassan. I think the same channel. Yeah, there's only one side. Yeah. All right. I mean, is that surprising for anybody? Yeah. Had you heard about this, KG? There may not be loss in information due to sampling process. Ji Hassan.
Sir, I am surprised because मैंने chat में भी लिखा था कि if you have a frequency like a peak हो, जो आपके sampling rate से भी ज़्यादा हो, तो वो peak उसमें capture नहीं होनी चाहिए.
Yeah.
So
that's why I put those caveats, or I put those disclaimers there. So as long as the x of t, xc of t satisfies some conditions,
okay,
there will exist a sampling frequency, and if that's a sampling frequency threshold, such that the sampling frequency is more than that threshold, that will ensure there's no loss in information.
Right.
And those constraint in the input signal is that the signal must be band limited, right? That's the constraint. And I'll touch upon this very slightly in one of the lectures, subsequent lectures. Right? Okay. Right. So if you're surprised, all you can do is just type "I'm surprised" in the back box, in the chat box. This ha 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 won't count in the CP, by the way. Okay. All right. So maybe more to say. Later. Okay, so I'm going to go ahead and now, Jeetala.
Is this like the no loss is because जिस तरह अगर हम sign को sample करें, we know it's a sign, so we can just recover it later on. Is this how it works?
Yes.
Okay.
But yeah. I mean, how do you sign को sample करें? What do you mean by that?
I mean, हम sign के discrete time पे लेंगे ना उसके points.
Yeah.
So we have a sine wave, and we know it's a sine wave. So all we need to do is just join the points इस तरह graph में करते हैं.
Yeah.
And there's a very high chance that we get the original signal.
But the only question is, how do you join? Right. So do you join linearly? That's piecewise sort of a linear interpolation. But it turns out that whenever you join like a sine. ये करना चाहिए यहाँ पे. That's what.
Yeah, we know it's a sign, so उसमें पे we won't do that.
Yeah, if you knew it's a sign, so then you could always do it. Right? And you did not know the frequency. That's the entire key. Maybe that's something you can brainstorm on. And maybe you can think about this on your own. And that would be, if you come up with a solution, that would be like you've derived Nyquist's theorem all on your own. And that should give you a sense of achievement. Talha, you're right in the right direction, by the way.
Thank you.
Okay. Achha. Now, what I want to do next is to talk about some background material, because this is something that we're going to be using a whole lot. So I thought, maybe I spend some time on this, and that's on geometric series. or sum of geometric series, right? So I want to start out with the following mathematical notation, right? So if I tell you so n, sorry, I equals 0 to n minus 1 r raised to power I. What does this mean? What does this mean? Can somebody try to, I just want to get a feel of KG. Is this something which is familiar? I mean, when you look at the summation, इसका क्या मतलब है? It should be familiar, right? It's a geometric series, right? I mean, whenever you see an equation, right? So the first thing you should, सबसे पहले ज़हन में क्या इसकी visualization आनी चाहिए कि हो क्या रहा है, right? What's actually going on, right? So that you should try to make that connection. And people say it's a sum of r raised to power n minus 1 terms. So this is actually, if I just write it out, I mean, this is a fancy way of, or a compact way of just saying that this is actually equal to r of 0 plus r of 1 plus r of 2 plus r of 3 dot 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 all the way up to r raised to power n minus 1, right? So this is what this notation means. This is a finite sum, right, of these values, right, which the index starts from I equals 0 and takes on values over the integer side. That's important. I mean, takes on values over the integers, just like we did in the Fourier series, right? Goes all the way up to, the index goes all the way up to n minus 1, right? What is this equal to? I mean, what does this sum evaluate to? What does this series evaluate to? And there's a relationship for that. I'm not going to prove that relationship. I'm just going to write it out. The proof is, by the way, in the end of chapter problem egg. Proof kare. So anybody? Any semblance of that relationship would suffice as well, right? Right. So Daniel says a naught upon 1 minus r. Not exactly. So Mehreen, do you want to say something?
Sir, I think we're going to use the formula that we have for the geometric series.
Yeah. And that formula would be is close to what you, common ratio R, close to what Daniel says as well. Not exactly though. Right. So Musa is almost there. Right. So this is, I mean, the way I write it is, I think Musa, okay, exactly same. There's no A here, by the way. Right. So A equals 1. Excellent, Ibrahim. Right. So this is 1 minus R, and in the denominator, and the numerator, this is 1 minus r raised to power n, right? So this is what this geometric series sums to, right? So, okay, so this is equation number 1. Or let me say, Kiji, this is the first result. So this is the most fundamental result. Now, if I just say, what is this equal to? A equals 0 to n, or actually I equals 0 to infinity r raised to power I. What is this equal to?
Sir, ये 1 over 1 minus r होता है?
Yes, this is equal to 1 upon 1 minus r. But so A equals 1. I mean, so people just keep on referring to A. That's perhaps because they sort of have this memorized in their heads. वो A वाला कोई formula था. So we don't have A here. I mean, A equals 1 in all of these cases, right? But this is equal to 1 upon 1 minus r. Is this always equal to 1 upon 1 minus r? Right? And I claim that this actually equation, this 2 can actually be derived from 1. Right? 1 is enough for you to know what 2 is. How so? Yeah, unless r equals 1. Exactly. Unless r equals, so r equals 1 doesn't make sense. R is less than 0, right? So you're there. So if it turns out that this holds true only when Musa, not when r is less than 0, but the absolute value of r is less than 0, because remember, r could be negative as well. And if r is negative, for example, -2, this wouldn't hold.
Yes, sir.
Right? Why would it not hold? And that's my next question. And that is clearly visible from this over here, right? If you see, if absolute value of r is less than, sorry, is it less than 0? मैंने क्यों कर दिया? It's less than 1. I cannot, right? If absolute value of r is less than 1, what can you say about r raised to power n, or limit n going to infinity r raised to power n? That is equal to 0, right? That is going to converge to 0 as n goes to infinity, because r is a number which is less than 1, between 0 and 1, let's say. Take care. And you keep on raising it, it can become smaller and smaller and smaller, so it decays, right? And as n goes to infinity, this turns out to be 0. But the other hand, if r was greater than 1, that's where it's going to diverge, right? So the equation number 2 can actually be derived from equation number 1, right? And this is important, holds only when absolute value of r is less than 1. Otherwise, this series diverges. Otherwise, series diverges. All right. So continuing with that background. Now, let me up the game a little bit, right? Which is, let's say I have I equals -2. That's what I might be. I equals n1 to n2 r raised to power I. What is this equal to? Where n1 and n2 are not infinite, they're finite values. So how do you evaluate this? Can you evaluate what this is just by using the result number 1? Can we do some manipulations? Ji Musa.
So what if we subtract the term from I is equal to 0 to n2 and then minus I is equal to 0 to n1?
Good. So that's one way to do it. I would rather push for a much more elegant solution. Right? What you're saying, Musa, is excellent, right? So Musa suggests this is equal to right, I equals n1. So I equals 0 to n2 r raised to power I minus I equals minus क्या होगा? 0 to n1 minus 1. Right? So that's one way to do it. But what if n1 was negative?
Oh, yes, sir.
Then this doesn't hold.
Yes, sir.
Then you could have said even then you could have said something. You could have said then is the summation from minus that whatever that value was from n1 to 0 and then from 0 to n2. That could have been the case as well. But I would argue for a more elegant solution where you don't have to worry about yaar kaun sa negative hai, kaun sa positive hai, kaun sa bada hai, kaun sa nahi hai. All I know over here is that n2 is greater than n1, right? And I will make a change of variables, right? I will make a change of variables so as to bring this equation number 3 into a form that looks like equation number 1, right? And that change of variables looks like the following. So I want a new variable, m, as a function of I. And I want that change or replacement to be of the form such that when I equals n1, I want the new variable to be equal to 0. How does that happen? How can that happen? Here's how. So if I choose m equals I minus n1, right? Then I would ensure that when I equals n1, m turns out to be equal to 0, right? So if m equals I minus n1, then m equals 0 when I equals n1 and m equals n2 minus n1 when I equals n2, right? And this implies that I is equal to m plus n1. So therefore, this summation that we had, this series that we had, which is I equals n1 to n2 r raised to power I, this is actually equal to, when I do that some replacement, this turns out to be equal to m going from 0 to n2 minus n1. And here I have r raised to power m plus n1, which is equal to r raised to power n1, which is a constant as far as the summation is concerned, right? It goes out of the summation. And this summation is from m equals 0 to n2 minus n1 r raised to power m, right? Why was I able to bring this r raised to power n1 out? I mean, why is this thing out of the summation? Why is this out of the summation? Anyone? Right. Jim Hanu?
Certainly, I want to say the same thing, that it doesn't depend on m, though, like it can be brought out.
Yes, it doesn't depend on, it's not a function of m. So therefore it's a constant, so it can come out, right? Acha. And then I know from my first, right, first jo relationship thi, or first result, which is the r raised to power n1 is on the outside, and the series evaluates to 1 minus r raised to power n2 minus n1 plus 1 divided by 1 minus r. And there you go, right? So, I mean, the point I wanted to illustrate here is I don't need to remember a lot of these things, right? So, I mean, people tend to memorize कि यार अगर ये नीचे वाली ये होगी तो ये इसका आंसर ये है, ऊपर वाला ये होगा तो इसका आंसर ये है, अगर कांस्टेंट है तो इसका आंसर ये है, और ये the formula is this. You don't need to remember all of those formulas. Perhaps a formula that you may want to remember is just this one, which is the first one, right? So from here, I've been able to derive everything, right? So this is the right? So if you were to memorize, just memorize this. If you need to. I mean, otherwise you can derive this as well. Okay, so this was the background material that I wanted to cover on geometric series. Right. Any questions here before I move ahead? Okay, Hafsa. So, I mean, yes, Hafsa, you would get the same time. I mean, not some, but we have to, you have to take the difference depending on whether it's positive or negative. So you see, earlier I wrote something down, what Musa suggested. I mean, I would urge you to go that route as well and see you're going to get exactly the same result. Okay? All right. So basic stuff I'm going to continue. And the following stuff, actually, I'm going to perhaps go over quickly because this is something we've seen in continuous time signals. And the ideas are similar, except all of the integrals are replaced with summation. So we're talking about signal energy and power. So just like we have the concept of signal energy and power in continuous time signals, we have the same set of ideas which apply to discrete time signals as well. If you want to see that a signal strong hai ya nahi hai, I mean, what is the energy inside the signal? I mean, without really caring for is this thing that we're evaluating, now, is that energy in joules or not? That's just a mathematical quantity that tells us, okay, is a signal big or is a signal small, right? And the signal energy is defined as summation n going from minus infinity to plus infinity x of n absolute squared, right? So I mean, the only way this is different than continuous time is that you're replacing the integral with a summation, right? That's the only difference, right? Other than that, it's exactly the same. What you're doing is you're taking up the entire signal from minus infinity to plus infinity, for these discrete values of the independent variable. You're squaring that, absolute squaring them up and just adding that. So this is where the series evaluations are going to come in handy, right, as we're going to see, right? Similarly, if somebody can tell me what the power is going to be, I mean, it's trying to the same sort of ideas. So Daniel, we've not done discrete time Fourier series yet, so we don't know what the equivalent of parsecs is, and we're going to come to that later, right? But now let's just focus on what power is. And power kya hogi? What do you think? Anybody who's not spoken yet and who would like to speak? So what do you think the power? I mean, right? So power is what? Power is defined as a normalized energy, right? So when we say so power was in continuous time. We say I'm going to evaluate the energy in a certain time period, and then I'm going to divide that energy by the length of that time period. That's the power in that time period. But if I'm evaluating over infinity, right? So I'm going to do the same thing, except that the length of the interval, I'm going to take that to infinity, right? So this is exactly what you do here as well, right? But in that limit, right? So the definition here, something close to what Manur is suggesting, is there's a limit capital N going to infinity, and let me compute the energy from minus n to plus n, right? So this is x of n absolute squared. And then I need to divide this by the length of the interval. Now, what do I mean by the length of the interval? The length of the interval in this case is just the number of values that are there in that summation, right? So in other words, if I just take the signal from minus n to plus n, right? So I have some number of values within this interval. What is the number of values that I have within the interval from minus capital N to plus capital N? What is the number of integers within this interval? Where capital N is an integer, by the way. Right, I mean, forget about taking that limit to n going to infinity first, right? Right, Maz says 2n. Tala is 9, is just an illustration. I mean, so, right, so 2n is not right, right? Hamza, Rashid, excellent, Hamza. This is 2n plus 1, right? This is 2n plus 1. And this is how things are different in discrete time, right? So, I mean, the number of values between minus 2 and plus 2 are actually not 4, but 5, because you need to count the first one as well, right? So the number of values between 0 and 3 are actually 4, because 0, 1, 0, 1, 2, 3, right? So these are 4 values, right? So this is 2n plus 1. Not that it matters, by the way, when you're taking the limit, but to be precise, this needs to be 2n plus 1. Let me, this is 2n plus 1. So this is the definition of the power. This is the definition of the power, right? Let's do some examples to, 2 examples in particular, right? So this is example 1. So when I say it, this 2n plus 1 does not matter. Why does it not matter? This plus 1, even if I don't have this plus 1, it won't make a difference.
Sir, because n goes to infinity.
Yes, because n goes to infinity, and plus 1 is just a finite number, doesn't make a difference, right? Zan also said, Kitty, what do you mean by taking the length to infinity? Zan, have I answered your question, or do you want to elaborate on your question furthermore? Zan, I think, left. Yeah, I did. Okay, so this is the first example, and I say, okay, what x of n is equal to 4. Achha, by the way, before I do this, I mean, there's usual definitions. Energy signal. What are those signals? Those signals in which the energy is less than infinity. In other words, it's a finite energy signal. And then power signals are what signals? The same ideas as that we use in continuous time. Those in which the power is non-zero and finite, right? So that's the definition of energy signals and power signals, just like what we had in the continuous time case. And these are the examples. These are two examples that we're going to discuss. The first example is x of n equals 4. Right? What is the energy in this signal? The energy in this signal is summation n going from minus infinity to plus infinity, x of n absolute squared. What is this equal to? What is this summation equal to when x of n is equal to 4? What do they mean by x of n equals 4? I mean, that just means okay, this thing here, x of n equals 4, the signal is equal to 4, or is flat, right? Equal to 4 for all integer values of n. It just stays flat all the way from minus infinity to plus infinity is just equal to 4. 4 har jagah pe 4 hai, right? And you're required to compute the energy in the signal. So Manur, what would be the energy in the signal? It won't be 16. Why would it not be 16? Because what you're doing is this is n going from minus infinity to infinity, and x of n equals 16. What does this mean here? And this is also important. इसका मतलब क्या है? इस notation का. You're summing 16. How many times? Infinitely many times. Right? So this is 16 plus 16 plus 16 all the way up to infinity. And therefore, this goes to infinity. And therefore, this is not an energy signal. Right? Maz, why do you say it's 0? I mean, I could have said this is 0. Perhaps what you're confusing this is the following. N equals minus infinity to plus infinity. And if this was the case, then I could have said, oh, perhaps this is equal to 0. And this turns out to be 0. Right? Because what you're summing up here is, okay, 0 plus 1. Yeah, and then 0 and minus 1. I mean, everything cancels. So every positive value cancels with a negative value. Therefore, the sum is 0. But this is actually not what we're doing, right? So what we're doing is we're summing 16 how many times over n? Infinitely many times. And that's why this turns out to be 0. Or this turns out to be infinity. Now, what about the power? And that's also that's more interesting, but not too hard, right? So this is limit n going to infinity just by the definition. This is 2n plus 1, and this is summation n equals minus n to plus n, and once again I have 16 here. What is this equal to? What is this going to be equal to? So this is once again limit n going to infinity. This is 1 upon 2n plus 1. What is this sum equal to? Umar, why do you say 1?
So infinity over infinity हो जाएगा तो 1 हो जाएगा. The summation would equate to infinity or 1 upon infinity by
the first thing I want to say is infinity over infinity is not 1. Right? Because there are varying levels of infinity. So what is 2 times infinity divided by 2? Or sorry, 2 times infinity divided by infinity? I don't know. I want to see कि वो infinity पे कैसे approach कर रहा है, निचला वाला denominator infinity पे कैसे approach कर रहा है. Right? So that depends on us. Similarly, what is 2n divided by n as n goes to infinity? This is still infinity over infinity, but the answer is 2. Right? So let's see. Let me pick somebody who's not spoken yet. Ibrahim has not spoken yet, I think. J. Ibrahim, why do you say 32 by 3?
Sir, L'Hopital rule se maine.
Okay. Okay, I want to go to Maz. Maz, why is the answer 16? Maz, you have the correct answer.
Sir, because I think 16 को sum करें 2n plus 1 times, तो वो 2n plus 1 हमारा numerator में भी आ जाएगा, तो वो cut हो जाएंगे.
Excellent, excellent, Maz. So this is 2n plus 1 times 16. Right, the summation is 2n plus 1 times 16. And why is that? Because what you're doing is you're summing 16. And how many times are you summing 16? You're summing 16 to n plus 1 number of times, right? And so that's why this is equal to 2n plus 1 times 16. And Ibrahim, even if it was 2n, even if you took 2n, so then that would have been 2n divided by 2n plus 1, 16. And in that limit, as n goes to infinity, it would still be 16. Right? That would still be 16 in that limit, right? So in this particular case, this turns out to be equal to, this is limit n going to infinity, and this is 16, and therefore this is 16. I mean, what is left is not a function of n, and therefore this is 16. The power is 16 in this case, right? So this is a power signal, right? So therefore this is a power signal. Now let me consider another example. And this example is x of n equals a raised to power absolute value of n, right? Where, let me tell you that a is real and 0 is less than a is less than 1, right? So if I were to ask you to sketch this signal, what would that signal sketch look like? Somebody who's not spoken yet, who would like to venture a guess? Even if it's a guess. So what would a raised to power absolute of n look like? Right? So yes, it's an exponential decay on both sides. Because a is less than 1, right, it is a decay. Right? So if this is 0, this is where the signal is 1. Right? And then as n increases, the signal exponentially decays. But goes all the way up to infinity, right? So this is the envelope. What about the negative side? The signal is symmetric, right? Because there's an absolute value of n there, right? So when n equals -1, this is still a raised to power 1, which is less than 1, right? So this is still going to be symmetric. And this is -1, -2, -3, -4. Now, what is the energy in this? The energy, if I compute the energy, this should be n equals to -infinity to +infinity, x of n absolute squared. Therefore, this is n going from -infinity to +infinity. X of n is a raised to power absolute of n, and then there's a whole squared here. Now, how do I solve this? How do I solve this summation? Any ideas on how I should solve this equation or this series? Right, so I see this is summation n going from -infinity to +infinity. This is a raised to power 2 times absolute of n, right? And then what do I do? Ji Manu?
Sir, maybe separate like -infinity to 0, फिर 0 to infinity.
Excellent, right? So this is summation from -infinity to 0, and this is a raised to power 2 times absolute of n. And just make sure that when you separate this out, I think what you suggested, Manu, was going from 0 to infinity, and this is a raised to power 2 times absolute of n. And there's a slight bit of a minus, this is a slight bit of an error here in this. Can you spot that error? Anybody? Ji Musa.
Maybe कि 0 दोनों cases में आ रहा है.
Dono cases में 0 आ रहा है, right? So you're actually counting 0 twice, and that should not happen, right? So this is actually from 1, right? This is how summations are different than integrals, right? So if this integral was from -infinity to 0, minus infinity plus infinity, I could have split it up into from minus infinity to 0 and from 0 to infinity, and doesn't matter because 0 is 1 is a 0 minus 0 plus, I mean, doesn't make a difference, right? But integers, you have to be careful, right? So wait, the first is from minus infinity to 0, and the other one, therefore, must be from 1 to infinity. Otherwise, you're going to be counting 0 twice because it's a discrete value. Now, how do I evaluate this further, right? So then I see here, so this is equal to here, this is n going from minus infinity to 0. This is a raised to power minus 2n. And the reason is because when n is negative, the absolute value of n is equal to minus n. And over here, this is summation going from 1 to infinity, a raised to power 2 times n, because n, when n is positive, the absolute of n is equal to n, right? अब क्या करूं मैं? What do I do here? I mean, how do I resolve, or how do I solve what these, I mean, so once again, that's why I discussed that background material there, right? So you want to transform these finite or infinite series to a form that looks like something that you're familiar with, right? And what you were familiar with was the summation going from 0 to infinity, right? Not from minus infinity to 0. So you'd have to make a change of variables to ensure this now, or to transform it into a form in which the summation goes from 0 to infinity. So what kind of a change of variables can I employ here to do that transformation, right? So I would substitute here m equals minus n, so that summation going, instead of going from minus infinity to 0, it now goes from 0 to plus infinity. It's a flip in the sign, right? And here I would make another change of variables, and I say, let's say k equals n minus 1, so that when n equals 1, k equals 0, right? So this becomes m equals infinity to 0, and this is a raised to power 2 times m, and this plus this is k equals 0 to infinity, and this is a raised to power 2 times k plus 2, right? I just make that substitution, and this is easy to resolve. A raised to power 2 just goes outside, right? So this is a squared outside. Acha. What can I say about this first sum? When I say, okay, the sum is actually going from infinity to 0, I mean, what that means is, okay, this is actually counting backwards because you did a flipping in the sign as well, right? So, and flipping does not, I mean, as opposed to continuous time, flipping in the discrete time doesn't make a difference, right? If you sum from -1 or -3 to 0, or from 0 to -3, doesn't make a difference, because what matters is what are the things that are adding up. The direction is not important, right? So I can say, yeah, this flipping is really actually going from m equals, the summation is going from 0 to infinity, and this is a raised to power 2m, and this is a squared, and this is summation k equals 0 to infinity. This is a raised to power 2k. अब ये किसके बराबर है? I've not really resolved it to that form that we're familiar with. Here's how I do that. So this is m equals 0 to infinity. This is a squared, and then this is raised to power m. And plus this is a squared. This is summation k equals 0 to infinity. This is a squared, and then it's raised to power k. Right? And now I can do what I can do. So this is 1 upon 1 minus a squared, and this is 1 upon 1 minus a squared, right? And this evaluates to 1 minus a squared and 1 plus a squared here, right? And so this is your what were we computing? This was the energy, right? This was the energy. And the only reason why I went through this is to just, go through these exercise. And some of the comments, my response to those comments in the chat box would be, okay, how do you cater to these? Okay, if you want to say, I don't want to do these mistakes in the exams. What's the solution to that? Yes, that's the solution there in the chat box. You must practice, right? So you do this 2 or 3 times, and that's going to be enough, right? Literally, 3-4 dafa kare, and it's going to be it's going to be ingrained in your head. You're not going to be making those mistakes anyway, right? Right, and of course that as well, Manur. Right. So is this what about the power? What would be the power? What do you think the power would be? Do I need to go through this entire set of calculations again? Or is there something I could just use reasoning to conclude what power should be? Right. So since the energy is finite, we know that the power must be 0, right? So P is 0. Right. So this is less than infinity. If this is less than infinity, the power over that infinite interval must be 0. Right. So this is this particular signal is an energy signal. Okay. Just to ensure, KG, so let me leave off with an exercise. It's just a continuation. And I'm going to stop, which is, KG, solve the problem above. For the case when A is complex and the absolute value of A is less than 1. Right? So, whatever we did here, we specifically stated somewhere, okay, A is real, right? So this is what we stated, that A is real and A is between 0 and 1. Right? So this is where we stated A is real, right? Can you now extend the same ideas to the case when A was complex, but the magnitude of A must be less than 1? Okay. Now, there was a question in the chat box, why is the power 0? The power is 0 because the energy is finite, right? Because if the energy is finite and you're computing the power, so the energy computed over an infinite interval is finite. If you need to compute the power is just the energy divided by the length of the interval. And the length of the interval is infinite, so a finite number divided by an infinite number is 0. Does that make sense, Ibrahim? All right. Okay, I'm going to stop here. Are there any questions?